Welcome to the 1952 Nobel Prize in Physics, which went to Felix Bloch and Edward Purcell. And what they did was they discovered a new method for making really precise nuclear magnetic measurements. Now, and because of that, there were a whole bunch of new discoveries that kind of came flying out. Now, nuclear magnetic measurements, if that sounds a little bit familiar, and you're not wrong, the 1944 prize went to Isidore Rabi, who discovered that phenomenon. And what these two gentlemen did was they made the measurements much more precise, which is very important given what this stuff is used for. Now, let's take a little bit closer look at what happened in 1944 as a little bit of a reminder, and then we'll dig into how 1952 was different. And this one has absolute importance to your life. You probably either know someone who has used this or had it involved in a medical procedure somewhere. It's involved in life-saving events all the time. So let's take a look at what these two gentlemen did and the shoulders of the giant they were standing on that won the prize in 1944. Now, Isidore Rabi's experiment looked a little bit like this diagram here. What he did was he passed a molecular beam through a magnetic field, and the rotational conditions of the molecular beam before it went through the electric field and after were different if you introduced it to a radio wave as well, and it would be changed in accordance with quantum mechanics. But it also emitted some signatures that were very specific to the molecules, to the atoms inside the molecules of the molecular beam. So you could tell exactly what was in that beam, whether it was two hydrogens, three hydrogens. You could tell ratios of different chemicals that were inside there, which allowed you to pinpoint exactly what your molecular beam was made of. That gives you an opportunity to use that phenomena to go on and look at ways to determine exactly what molecule is in everything from your favorite coffee mug to your phone case to the tumor that's inside your head. Now, it wasn't quite ready for prime time, but that is the basis for what MRIs are today. Now, this is the phenomena, but now let's go look and dig and see what these other two guys did to deserve a second Nobel Prize in this same field. Now, one of the things I left out about Rabi's design was that it only works in vacuum. It only works if you've got the molecules moving in some beam going through an electromagnet. That doesn't work really well if you're a human being trying to get an MRI, because you're not going to take the organ out of the human being, turn it into a beam, and that's not going to work. So what Bloch and Purcell did at two different universities at virtually the same time was found a way to do it in situ. So could you do it in a solid material? Because that really is far more useful than doing something in vacuum. In vacuum, you could discover the phenomena, you could do all kinds of things, and some things in vacuum are very useful. But when it comes to trying to build an MRI device to go off and use that for medical purposes, in vacuum is not really where you want to put your patient. So let's take a look at how these two did it, because they actually came at it from different directions, which is even more interesting. Now, Purcell and his team used a resonant cavity filled with paraffin wax and RF loops. They drove it around 30 megahertz and showed that the resonance of hydrogen can be gotten after you put that entire thing in an electromagnet. And that's a great thing, because now you've got this solid material that you can get the same signal out of. You still have to put it in an electromagnet, but we're coming further than using a molecular beam. Now, Bloch and his team used a smaller device. They used a cc of water in a glass bulb, which they wrapped in a transmitter and receiver elements, and they operated it around 8 megahertz, and they induced a magnetic field, and they measured hydrogen. Now, that's also very interesting, because if you look at these two experimental approaches, there's a little bit different. Purcell did what's known as an absorption experiment. Bloch did what's known as an induction experiment. Purcell was working in the world of quantum mechanics. Bloch was working in the world of classical physics, and they got the same answer. That's exactly what you want to see in physics. You don't want to say, well, in classical sense, you get this, and in a quantum sense, you get that. All of those need to agree, or you've still got a problem someplace, because we like it to agree in all cases, not just in one or another. And that is why things like the grand unified theory are still a problem, because there's parts of physics that don't match other parts of physics, and we're trying to sort those things out. Now, all of this is great, because what this and what Bloch and Purcell and those that came before him did was they gave us the phenomena now in solid form to do what is now MRIs in the hospital that are saving lives every day. We're getting closer and closer to that technology, but without these gentlemen to learn from, we would have may have never gotten there. Thank you for listening. I do hope you've enjoyed this video. Don't forget to click like and subscribe and all that fun stuff that helps us out with the YouTube algorithms, and we will see you on the next one.